Hello, my name is Alexander Fabisch. I'm a researcher at the Robotics Innovation Center of the German Research Center for Artificial Intelligence. My work focuses on machine learning for robotics, and I'll give a talk about learning to grasp. So this is one of the fundamental skills that a robot usually has to possess to deal with manipulation in the real world. So the outline of this talk is as follows. I'll start with an introduction to grasping and behavior learning, and then I'll talk about two categories of behavior learning and give examples of how machine learning can assist the grasping process performed by a robot. To give some introduction to grasping, the things that we need to grasp with a robot are, first of all, of course, grippers. And there's a multitude of different grippers for robotic systems. Just a brief overview is here on the slide. You see that there are very simple systems with, for example, 2 fingers and just 1 degree of freedom. And there are moderately complex systems like the grasper that you see in the middle of the slide with 3 fingers and 9 degrees of freedoms that have to be controlled. And then there are very complex systems like the dexterous hand from Shadow, which has 5 fingers and 24 degrees of freedom, of which 20 are actually controlled. What you need as well are robotic arms. And here are just 2 typical examples of robotic arms that are used in research at the moment. One on the left from Universal Robots, the UR5, which has 6 degrees of freedom and can lift up to 5 kilograms. And on the right side, you see the KUKA LBR EVA, which has 7 degrees of freedom and can lift up to 14 kilograms. And what you need as well, of course, are objects that you can grasp. And here's just one example of objects that you might encounter in the real world. And these are for example, a hammer, so some sort of tools, all sort of balls of fruits, and also cutlery and so on. So these are completely different objects that you might want to grasp, and they all have to handle them all differently. And these are taken from a benchmark set, which is called the YCB benchmark. And these are actually objects that you can buy physically, and you can also get meshes to use them in simulation. And these are designed to actually evaluate grasping behaviors of robots. And they can also be used to train robots. So how do we actually implement grasping? And one approach is we can learn it for a robot. And there are several categories of behavior learning methods that you could use. For example, you could use supervised learning approaches, which includes, for example, imitation learning, which means, for example, you could demonstrate a behavior as a human, and that can be transferred to the robotic system. That also means that includes a human teleoperating a robotic arm, and that motion generated by the human could also be imitated, for example. There are self-supervised learning approaches where you don't have to teach the robot how to move exactly, but the robot can generate a label for each grasp that it tried to do, for example. And then it can learn from these labels what are successful grasps and what are not successful grasps. And then there are more independent approaches like reinforcement learning, which basically deals with learning behaviors directly. And also kind of related to that is black box optimization. Actually, some black box optimization algorithms can be called reinforcement learning algorithms. So we don't learn from raw data. We cannot just throw data at the robot, but we also have to provide some kind of expert knowledge to the system. For example, labels for the data, if you have to provide expert demonstration or a reward in the world of reinforcement learning, or some kind of fitness function. And maybe you also need some kind of simulation that we can use to perform trials. So why do we learn behaviors at all? There are several reasons why we want to apply machine learning to the problem of learning to grasp. For example, machine learning algorithms are usually quite well in the presence of uncertainty and noise, because they can learn from the data. They can also learn to handle uncertainty and noise. That is something that classical planning approaches usually don't consider. We can also use machine learning when there are inaccurate models. And also for grasping, there are not always accurate models of the world available, especially when we have to handle unknown objects. And usually, when you handcraft a solution for some specific purpose, then it's sometimes even worse than learning it directly. Also, programming is something that might become very complex or even infeasible in some situations. Also, sometimes you don't need a perfect solution. A simple heuristic is often sufficient to solve some behavior learning problem. When we categorize the approach that we will discuss here for learning to grasp, we can distinguish between approaches that deal with the perception part of grasping, finding the object, locating it, and then generating the appropriate trajectory. And the last part, generating the trajectory, is actually more the action part. And you can either learn the perception part only, or you can learn the action part only, or you can learn both at the same time. So what would the perception part include? That would include, for example, handling depth images or RGB images. You can also use force torque sensors to react to the forces that you measure during grasping. And then what you would generate from the object location or from the perception part is an appropriate or corresponding grasping trajectory. And that could be, for example, the Cartesian reference, or joint positions or velocities, or you could also generate torque commands for the robot. So usually what we do is not just learn everything end to end. There are several ways of combining learning methods and classical methods that we've seen or know from robotics. For example, you could combine object detection from classical computer vision with learning a trajectory. Or you could learn the object recognition part and then just generate a grasping trajectory with a planner. Or you could use an object detection method, a planning method, and you could only learn the grasp primitive. There are a lot of ways to do that. We will just see some examples of how you could combine classical approaches and machine learning approaches. We will take a look at 3 different papers in this talk, and those have completely different approaches. Let's start with supervised learning. First of all, I would like to explain what supervised learning actually is. First of all, you need some kind of training set for supervised learning that consists of data pairs which represent the input and the desired output of the function that you want to learn. You put that data set or that training set into a learning algorithm, and that learning algorithm will generate some kind of hypothesis for you. That hypothesis, in the end, takes new data X and predicts Y hat. This is something like a label, or also maybe a continuous value. And of course, you need pairs of X and Y for training to teach the learning algorithm what would be an appropriate mapping. Now I'll give a short introduction to neural networks, which is one of the most prominent supervised learning approaches. So why do I do that? Because neural networks are used in all of the papers that we present in this part of the talk. And neural networks are basically there for about 70 years already. So the neural networks are one kind of machine learning approach that is inspired by the human or animal brain. It has been researched since the 1940s of the last century. And basically, the fundamental algorithms that we use today have already been developed in the 80s or 70s. So one very prominent buzzword of the last years is the so-called deep learning, which is basically neural networks with many layers. And that has been basically invented in the year 2006, when the first publication introduced this term to the research of machine learning. So, but basically deep learning is just neural networks. And neural networks have fundamental building blocks, and they are called neurons. Here you see this schema of a neuron. What they do is they take inputs, here denoted as x, with an index I, and they compute a weighted sum of their inputs. And the weights that you see here, those weights W, actually represent the knowledge of the network. So by changing the weights, we change how the network predicts its output or generates its output. After computing this weighted sum, which is called the activation of a neuron, we pass that activation to a nonlinear activation function, which is called G here. Usually it's nonlinear, but it could also be a linear function. And after we do that, we obtain the output Y of the neuron. And what you do then is you don't just have one neuron, but you organize neurons in multiple layers, usually. So here's a schema of a more complex neural network, which consists of multiple layers. Those are densely connected or fully connected. That means we have on the left side an input layer. The input neurons are denoted by X. And these input neurons send their output to all of the neurons in the following layer. And they also send their outputs to all of the neurons in their following layer. And so on until we compute all the outputs in the output layer. And this is one specific form of a neural network, which is historically named the multi-layer perceptron. And we could also replace several of these layers with different connectivity patterns. But how do we actually learn such a neural network? Again, we need some kind of training set. In the training set, we have pairs of inputs and outputs. The inputs are called X in this sketch. And then we have desired outputs, T. And we can pass the input to a neural network, which has some weights W. And the neural network will compute an output Y. And we can compare the output of the neural network with the desired output to compute some kind of error. And that is the objective function for an optimization problem that we want to solve. So there are a lot of ways how to do that, how to solve these optimization problems. I will not go into the details. I'll just refer you to some neural networks libraries that you can use to train a neural network. There are, for example, Keras in Python. There is also in Python, there's TensorFlow, and you could also use other libraries on different programming languages. MXNet is also one of the libraries that are used quite often. And you don't have to implement that on your own, usually, only if you want to develop new forms of neural networks. you can just use it, and you don't have to understand how the optimization works at all, but it helps, of course. But we won't go into the details now. So what distinguishes modern neural networks from the neural networks that we already had in the 80s? What is the same is that neural networks are usually organized in layers, as we have seen it before. They are, for example, those fully connected layers that we have seen. They are also convolutional layers that resemble closely the convolution that we use in computer vision very often. We'll go into the details on the next slides. Then there are recurrent layers that contain not only connections to the next layers, but also connections that are going backwards to previous neurons. One example is the so-called long short-term memory. And there are also a lot of other layers available at the moment. Modern neural networks are also often used to train them with GPUs. So graphical processing units are very efficient at computing a lot of things in parallel, and that's actually what you can use to train neural networks. They also have many layers, which makes them actually deep neural networks. For example, in the current state-of-the-art, we have seen network architectures that contain 100 or even 1,000 layers. They are also trained on very large data sets. In image or computer vision, we have data sets containing like 1 million or even more images. And there are, of course, also some additional tricks that we learned. For example, there are some activation functions that we can use to improve the training process. For example, rectified linear units are one very successful approach. Also, we have found better regularization methods. One of them is dropout that improves the generalization capabilities of a neural network. Also, batch normalization is a layer that helped a lot in simplifying the optimization problems for neural networks. So, more in detail about the convolutional layers. Maybe you know from image processing or computer vision that there are convolutions where you can take an input image and convolve it with a convolutional kernel and then generate a new output image. Those convolutions can, for example, be used to detect edges. And how does it work? You basically have a convolutional kernel that has a small size, maybe 3 by 3. You take the input image and move it over the input image. And when you're at a certain position, you take all the or subset of the input image and do an element-wise multiplication of the convolutional kernel and the input, the part of the input image. And then you sum up the result and write it to 1 pixel of the output image. And then you move the convolutional kernel over the whole input image. And you can imagine that this can also be interpreted as a neural network. For example, the convolutional kernel can be the weights of a neuron. And that means basically that you have a lot less connections than you would have in a fully connected layer, and that you share certain connections among different neurons, because the convolutional kernel is not only used for 1 pixel, but for all pixels of an output image. And usually we don't just do 1 convolution in a convolutional layer, but we have, for example, 200 convolutions that we apply to some input image. That's basically how a convolutional layer works. And that the great benefit of a convolutional layer is that you can process much larger images, for example. So it's basically designed for 2D data, but also could be used for 3-dimensional data. And you usually also can train much deeper neural networks than the networks that you would use if you use densely connected layers. Because the gradient is much larger in the input images, which was usually a very big problem 20 years before. And that is something which you don't have with convolutional layers. So, and all the following approaches make use of neural networks. The following doesn't use convolutional networks, but it will use fully connected layers. So this is the first paper that I'll present here to detect grasp positions in an image. It's published by Lenz et al. In 2015. It deals with the perception problem of grasping only, not with the action. It is a supervised learning approach, so there has to be some person who labeled all the data for the robot, and it doesn't contain anything related to reinforcement learning. So this is a paper, and what we will generate with this approach is those grasping rectangles that you see here in the image, and those basically represent how the gripper of the robot, it is a two-finger gripper, has to be oriented to grasp an object. So how does it work? In detail, we have two neural networks that are detecting those grasp rectangles in the image plane. The first one will exhaustively search over the whole image and rank grasping candidates. This is a small neural network. This has to be small because it will really exhaustively search over all possible options. It takes 4,032 inputs. Then it has 50 neurons in the first hidden layer and 50 neurons in the second hidden layer, and then will produce just one output, which gives you some kind of grasp probability or grasp success. The output is scaled between 0 and 1. Then we have a larger neural network, which contains 200 neurons in the first hidden layer and 200 in the second hidden layer, which is more expensive to evaluate, but it will give more accurate results. That's why we take the first 100 candidates, the best candidates given by the first neural network, and rank them, and then we take just the best candidates to actually perform our grasp. Then we just have to generate an approach vector for the robot, and then we can generate our grasp trajectory. So what do we need in terms of sensors? For example, if you see this robot here, on the left top of the image, you see its sensors, and basically what we need here are a camera on the left and a depth camera on the right. For example, a Kinect camera, which provides you with RGB data and depth image, will be sufficient for this approach. And then we have to apply some kind of data pre-processing, which is very complicated in this case. So we will take the raw sensor data, pre-process it, pass it to a neural network that will rank our grasping rectangles, and in the end, we will find out the best grasp. So how do we pre-process the data? First, we convert the RGB channels to YUV, which separates the intensity and the color information of an image, which is beneficial for this approach. Then we can also compute the surface normals of the depth image, which will also be used by the approach in a later stage, but it also provides useful features to the neural network. Then we apply some kind of whitening. For example, in the depth image, we do a patch-wise normalization. Then we do a feature-wise subtraction of the mean. And then we divide the features by the standard deviation in the corresponding channel, for example, the red channel of the image or the Y channel. Then we have to preserve the aspect ratio of the image to give it to a neural network, so we'll resize it to the appropriate size. And then we have to scale up the magnitude of the inputs so that the neural network is not confused. So what we do is we take those 7 channels, YUV of the image, of the RGB image, and then the depth image, and then the surface normals. And then we pad it to the size of the neural network with zeros to keep the aspect ratio of the original image. So there's a data set available that has been published by Lenz et al. And it contains 1,035 images with 280 objects. And each image is annotated with several grasping rectangles. Some examples of the objects and the images can be seen at the bottom. So how do we then generate the actual grasp? First of all, we start with this grasping rectangle that has been determined with the neural network. You see it on the left bottom of the page. And then we have to pad it and resize it to give it to the neural network. And then we search for the minimum depth point in the image in the central third. And that is assumed to be part of the object that we want to grasp. So here again, we need the depth image. Then we compute an average surface normal around that point, and we can use that to generate a grasp, an approach vector for the grasp. And we can compute the grip orientation from the orientation of the rectangle in the image. And before we actually grasp an object, we shift the pre-grasp pose about 10 centimeters on the direction of the approach vector. And then we move closer to the object and just close the gripper. Because it's a two-finger gripper, this is very simple. So, in summary, this approach has some advantages. For example, it generalizes to several different objects. It makes use of rich sensory data, the RGB-D images that we just saw. But it also has some disadvantages. For example, we have to do an exhaustive search over all possible grasp rectangles before we have the best candidate. This is not really computationally efficient. Then it does not generate a trajectory for grasping. So we still have to make use of a grasp planner or some kind of planner to actually generate a trajectory for the robot. And it's also not proven to be robust in cluttered environments. So we'll take another look at how we could learn to grasp. This approach, published by Levin et al. In 2017, is called hand-eye coordination, and you will see why in a few minutes. It only deals with a perception problem again, but it generates also some kind of waypoints. And it is also a supervised learning approach, but this time the labels are generated automatically. This is a paper, if you want to read more about that. And you need some kind of hardware configuration to do this. For example, you need a robotic arm. In this published paper, they had 7 degrees of freedom. They had a 2-finger gripper, and there was a camera mounted over the shoulder of the robot so that it could observe the environment of the robot. And they had a bin in front of the robot that contained multiple objects. And what they did is they trained a neural network which predicts the grasp success probability. It is trained from successful and failed grasp attempts. It basically takes an image of the bin in front of the robot and an image before it grasped and an image at the current point in time, and also a motor command that the robot could execute, and then it predicts the grasp success probability for that motor command given the current scene observed by the camera. The neural network consists of overall 16 convolutional layers and also some pooling layers, and are basically there to reduce the dimensionality of the data. And after that, there are two fully connected layers. And because the motor command has a very different structure than the image, it is first given to a fully connected layer, and then the size of this output is repeated multiple times with tiling to get the same size as the image at this stage, and then the motor command is given to the main part of the neural network. There's also a dataset available at this website. The dataset contains about 800,000 grasp attempts from real robotic systems. Each grasp attempt contains about 10 steps. Not always, but the maximum is 10 steps. The data is collected from 14 different robots with varying tear and wear, and also different camera poses. So you can assume that a neural network trained on this data is robust to some kind of variation in the configuration of the robot. Each sample contains the initial image before the grasp attempt, the current image in the process of grasping, and a motion command executed by the robot. And also a label that tells you if the overall grasping attempt was successful or not. So what do we get when we take a look at the neural network? Let us visualize the network for motion command V. The motion command consists of a Cartesian position given by x, y, and z coordinate, and a rotation of the gripper around its z-axis. So what you only can learn with the neural network, because the motion command is restricted, are pinch graphs from the top. So let's keep the z component of the anti-vector position fixed, and also the rotation about the angle, about the z-axis, gamma, let's keep it fixed. And we only vary the parameters x and y. Then you get the following plot, as you see on the right side. The color in this plot indicates grasp success. So there's some area where you can see there's a high chance of success, and it is more likely to succeed when you grasp in this area of the bin, and is less likely to succeed when you, for example, grasp at the top left of the bin. So how do you find the best motion command now? So you can think of just pick the position on the bottom right, but how do you get to that point? You don't immediately see, even if you have more dimensions, like a 4-dimensional space, you don't immediately see how to get there. And that is what is solved in this approach with the so-called Cross-Entropy Method, CEM, which is a black box optimization approach, which basically means you have some function f, which takes parameters theta, and you want to change these parameters theta to maximize this function. And what you want to maximize in this approach is the graph's success. And what you want to change, these parameters theta, are actually the motion command. And the basic idea of the cross-entropy method is that you have a Gaussian search distribution given by a mean and a covariance matrix. And in each iteration of the optimization, we draw n samples from this search distribution, and we take the best NE samples, where NE is smaller than n, to recompute the Gaussian search distribution. So we recompute the mean and the covariance matrix. And in the end, we obtain a better solution. The problem with CEM is that it only finds local optima. So what does it mean visually? If we have a grasp success prediction like this, also again with 2 parameters varied, then of course yellow indicates high grasp success, darker colors indicate low success probability, and you generate some kind of search distribution. You have to choose it initially, But then you draw 50 samples from this search distribution, and you order them by their fitness values, or in this case, by their grasp success probability. And you take the first 25 samples to recompute the search distribution. That's what you see on the second image. There we have drawn 50 new samples from the next search distribution, and this process is iterated over and over again. And in the third image, you already see that it's converging, and in the fourth image, the distribution is also closer to the optimum, and the covariance or the variance of the sample is smaller. And in the end, on the bottom right, you see that it almost converged. And those white samples that you see here are always the best samples, and those are reused to compute the new search distribution. So we can use that to optimize the grasp success probability. And then we can write down our surveying mechanism. So how do we actually perform a grasp? So we assume that we have 10 steps in the grasp process. And in each step T, we have given the current and the initial camera image and the network to predict the success. And then we can infer the optimal motion command VT star using our grasp success prediction network and the cross-entropy method. We can then evaluate a ratio called P here, which basically compares the grasp success of doing nothing and just closing the gripper to the grasp success probability of the best motion command. And if that value is greater than 0.1, that means doing nothing is quite good, then the gripper is closed. If that value is smaller than 0.5, that means we have to modify the optimal motion command, maybe to raise the height of the gripper a little bit and execute the optimal motion then. Or if it's between those two values, we just execute the optimal motion command directly. So this approach has some advantages. It actually generalizes to a lot of different objects and cluttered bins. It even generates some kind of intelligent grasp behaviors. For example, pre-grasp behaviors. So before it grasps an object that is maybe occluded by other objects, it will separate objects from other objects and then perform the grasp. It also makes use of rich sensory data, but it's sufficient to provide an image. You don't need a depth image, for example. It is a closed-loop approach and thus very robust against perturbations. It is also robust against varying conditions of the robot, wear and tear, and so on. The disadvantage is that when you apply exactly this, you need about 800,000 grasp attempts, which is very time-consuming and expensive. And we don't actually know which object the robot will grasp when you have multiple objects, so you cannot really tell the robot what to grasp. There's still also a lot of restrictions to this approach. For example, it's still limited to 2 fingers. Then it's limited to a specific location of the bin. It's limited to a specific robot. It doesn't really work to transfer knowledge from one robot to another one. And also the motion command is quite limited because it will only include translation and rotation about the z-axis. Not much more. You cannot really generate very complex grasping behaviors. We will take a look at reinforcement learning now. So reinforcement learning basically has 2 main components. There's the agent, and the agent acts in the environment. That means it can execute actions, and it will then change the state of the environment. And there's also a reward function involved that tells the agent how good it was to perform a certain action in a given environment in a given state. And this reward function is something that you usually have to implement, and it can be a very complex function, but the agent is then able to improve its actions over time and obtain a very successful policy, for example, to grasp an object. And we'll take a look at one specific publication. And this is about automizing learning. It is a paper from Gutzeit et al. Published in 2018. And this is not about perception, but about action. So about how to move a gripper to grasp a specific object. And this work also makes use of supervised learning, specifically about imitation learning, and also uses reinforcement learning to improve the obtained initial demonstration. This is a very complex learning system, which basically tries to automate all aspects of obtaining or learning demonstrations from humans. It uses a motion capture system, which produces raw data that has to be pre-processed and then generated trajectories will be segmented into individual building blocks of the behavior demonstrated by the human. Those segments will be imitated, and then a so-called motion plan will be generated. That motion plan will be refined by a reinforcement learning algorithm, and then we can also generalize that motion plan to a so-called behavior template, and we can store that in some behavior template pool and then execute it on a robotic system. So what we use here is marker-based motion captures. And for marker-based motion capturing systems, you often have to put those markers on the human, and you have to put a lot of cameras surrounding the human. For example, in this case, you see about 7 cameras in the room, and those cameras will track the position of the markers of the human. We can then transfer that motion to the robotic system. In this case, the example of throwing a ball with a robot is displayed. But before we can transfer the motion to the robot, we have to find some kind of mapping to the coordinate system of the robot. And also, when we have a robot, that structure might be very different from the structure of a human. So, for example, here you see the robot basically has a scoop attached to its end effector, or the end effector is a scoop. And the human hand is much more complex, has many more degrees of freedom, and many more muscles that control those degrees of freedom. So, capturing the movement and transferring that to another morphology, so another physical structure, that's called the embodiment mapping. And transferring the trajectory is usually kind of easy, but reproducing the effect is a hard problem because you have very different structures on a human and on the robot. So there's some kind of refinement required. And the way how we represent trajectories to do this refinement is we represent trajectories as dynamical movement primitives, DMPs. DMPs usually define parameterized trajectories. So we denote one DMP as a function P, which has which is a mapping from a state st at time t to a successor state st plus 1. And that state consists of a time, a position, velocity, and acceleration, for example, of a joint in a robot, or it could also be in Cartesian space, so Cartesian anti-vector position. And that P, that function P, the DMP, has some parameters, theta, that we can change to vary the form of the movement. And it also has some meta-parameters called nu here, which includes something like the goal of the movement. And it could also include the velocity at the end of the movement. DMPs do not directly define a policy or behavior. They just represent a mapping from one state to the next state, and then we have to generate an action for the robot. For example, a talk command. And that's also something we assume that is already there. So what are the advantages of DMPs over other behavior representations? We could also use a neural network to represent behaviors, for example. A neural network could also map directly from the state to an action that the robot has to execute, for example, a talk command. The advantage of DMPs is that they usually generate always smooth trajectories. And we can easily learn from demonstration. Even one demonstration is sufficient. It is a stable dynamical system. That means it doesn't diverge. Neural networks, for example, usually have the problem when you make several tiny errors in the action, those will accumulate and they will totally diverge from the trajectory that you initially learned. And DMPs also guarantee to reach the goal of the movement. And this goal is also a so-called meta-parameter of the DMP. That means you can set it manually. And the best thing of all is that you can even do reinforcement learning through policy search with a DMP. And a DMP with imitation learning and reinforcement learning is usually a powerful combination to generate new actions or trajectories for a robot. And they're actually easy to use. We implemented a library that we release open source. And you just have to, for example, if you work with Python, you could also use C++. You can import the DMP behavior module, and then you could create a new DMP object, initialize it, and you could get some demonstrated trajectory from some motion capture system or however you want to generate it. And then you can just call the imitate function of the DMP object, and it will be able to reproduce that demonstrated trajectory. You can also easily set several meta-parameters, for example, the start position and the goal position of the movement. And that's all that you have to do. And now let's take a look at what we can do with it. If we have a two-dimensional space and we want to generate a DMP that's generating the trajectory in this space, then we can give, for example, in the first image on the top left, we can imitate the blue trajectory, and then we can change the goal of the DMP and generate all the other trajectories that you see here, the green and the red trajectory, for example. And on the right side, you can see also the velocity profile. So how does the velocity generated for those spatial components evolve over time. And you can see that the farther you have to go, of course, the higher you have to set your peak velocity. And in the second row, you can see what happens when you change the goal velocity of a DMP. All of these DMPs basically start at the same position and reach the same goal, but reach the goal with a different velocity. And you can see that it has to modify the trajectory, of course, to reach this trajectory in the end, and at the same time reach the goal position. And on the right side, you can see the velocity profile. So those are just the absolute values of the velocity. And you can see that they reach exactly the velocity that you set manually. Also, you can change the execution time, but when you change that, then the trajectory will also change its shape. On the right side, you can then see that the blue trajectory with an execution time of 0.5 seconds is much faster than all the other trajectories, but also reaches the goal after 0.5 seconds. So what we can do now is we can learn with reinforcement learning. And reinforcement learning is a very broad field. There are a lot of different approaches, and classical reinforcement learning is usually called value function-based reinforcement learning. So we have a value function that tells you how good it is in a certain state to execute an action A, and based on that you can find the maximum the action that is the best one, which is very similar to the approach that we have seen previously, where we have a grasp success prediction network and we optimize the motion command. So that's basically very similar to how value function-based reinforcement learning works. And what we want to use here is so-called policy search. You don't have this value function that you need to generate a new action. You take a policy and directly optimize it to maximize the reward. And there are also hybrid approaches that use a value function but directly also optimize the policy. And the policy is what actually is generating your behavior. So some basic definitions. What is a policy? Policy P that has parameter theta maps from some state space to an action space. And in reinforcement learning, you also have so-called reward. A reward at step T basically is computed based on the state S at time T, the executed action, which is generated by the policy, and the successor state as T plus 1. Then you can sum up all of the rewards. There are different models how you do that. We just take the undiscounted sum of all the rewards to compute the return of an episode. And an episode is one trial of the robotic system. And what we want to do in policy search is we take this return, we use it as an objective function for an optimization problem. And that return depends only on the policy and its parameters. Basically, the policy depends on the parameters and the return depends on the policy. And you want to change those parameters of the policy to maximize your return. You can do that with policy search, and you're very close to black box optimization. So you could, for example, use the Cross-Entropy Method to do that. But you could also use different approaches, but they are basically all very similar. And one approach is a so-called covariance metric adaptation evolution strategies, which I'll briefly illustrate on the next slide. So what you see here is again a two-dimensional optimization problem. And basically, you want to optimize a quadratic function here, which has two parameters. Those could be parameters of a policy. And you want to find the red dot at the return landscape. And what you do is, again, you have some kind of search distribution from which you draw samples. This search distribution is represented by an orange ellipse, which basically represents an equiprobable line on the of the search distribution. And in the beginning, on the left top, you see that the search distribution is quite small. So it's very far away from the optimal parameters. And what you do then is, again, you sample from the search distribution, you evaluate several samples, several different policies, and you get the result, you obtain some kind of return, and you weight each sample that you have by its return to generate a new search distribution. And then you obtain the new search distribution represented by the green ellipse in each part of the image. And at the beginning, this is very small and it increases consistently until it covers also the optimal value and it's close to the optimal value. And when it discovers that it explores too much, then it shrinks the covariance matrix again and will eventually converge to the optimal value. Of course, this is also a local search approach. So if you have multiple local optima, you could also end up in some local optimum that's not equal to the global optimum. And this is how very many of these policy search algorithms work, or at least very similar. So with this approach, we have several advantages. We can generate very complex grasping trajectories with also very complex gripper behavior, for example. And we can easily modify meta parameters. So, for example, we could modify the goal position of the grasping process. And that means when we know the position of an object, we could easily adapt the goal position to the new position of the object. The disadvantages, of course, are obvious. We don't include any perception at the moment, but that could also be included with other approaches. So, to give you an idea of how that works, when we have a demonstration from a human, this human is actually grasping the object, putting it on the table, putting it back. So we have a sequence of different actions, and that first has to be segmented into different building blocks for the behavior. And then in the end, what's only interesting for us is the grasping movement. And that has to be labeled automatically here. And as soon as that is done, we can transfer to the robotic system. That won't work perfectly because a human hand is quite different in comparison to the robotic gripper. And there are some differences in the transferred motion because you have different spatial and temporal constraints on the robotic system. So what you can do is you can take a simulation and refine that skill with policy search. And you can see that here are multiple failing attempts. So it's basically learning by trial and error. And in the end, it will have some successful grasp attempt. And that can be transferred to the real robotic system. And in this case, we solve this perception problem by putting an Aruko marker on the object that we want to grasp, and we could perfectly determine the position of the object and set the goal position of the grasp accordingly. What we also tried is learning grasping from scratch with multiple objects, and that's what you see here with the same approach, but this time we modify the whole trajectory of the gripper and the complete arm, and we have about 15 parameters that we have to, or 15 degrees of freedom that we have to learn. And you see that it is able to successfully grasp multiple objects.